In this video lecture, I will discuss the Simpson's approximation, and let's get started by reminding ourselves the previous ways to approximate the area under a function, and we have learned quite a few. So we have a left endpoint, right endpoint, and midpoint approximations. Then we have trapezoidal approximation, and now we're going to learn the Simpson's approximation. And the main difference between these different ways is that in left endpoint, right endpoint, and midpoint, we use rectangles, and we use the fact that we just simply use the formula that the base times height is equal to the area of a rectangle. And in trapezoidal approximation, instead of rectangles, we use trapezoids. And when you have trapezoids, we use a different formula. The area of a trapezoid is this, and h in this case is the width of an interval. So the formula for the trapezoidal approximation somewhat looks like this. And what's going to be different in Simpson's approximation is that instead of using multiple rectangles or multiple trapezoids, we're going to use, let's say if we're going to have 3 points, so instead of trying to build trapezoids or rectangles, we're going to build some parabola based on 3 points. And the first question is, well, if we have 3 points through which the parabola passes, and one of them doesn't have to be a vertex, right? So we can have something like this maybe, right? So not a good picture, but the point is it doesn't have to be a vertex. And the question is, first of all, is there a formula that can tell us what the area is under the parabola? And if there is a formula, how are we going to use that formula to find the area under the curve? And turns out that there is a formula, and that formula, let me set up the problem. So the formula is telling us when and if you are given a parabola that passes through, let's say, 3 points. So let me just draw it out nicely. So something like this, right? Let's say we have it set up like this. So here's the origin. This point is at negative h units away from the origin to the left, or the x-coordinate is negative h. The right end point is h, and so both points are h units apart from the midpoint. And let's say we're given the output of the function at this point is y0, the output of the function at this point is y1, and the output of the function at this point is y2. And we have some function f of x here, which we're going to assume is a parabola. So it can be written as ax squared plus bx plus c for some coefficients a, b, and c. And the question is, do we know the area under this parabola? And the answer is actually surprisingly simple. It is yes. And if we do integrate this parabola, from negative h to h. So it's an algebra problem, right? So first we have to find this ax squared, a, b, and c. But then after we find it, if we integrate it, we are going to end up with something that is actually quite nice. It's going to be h over 3, or let me write it like this. It's going to be 1/3 y0 plus 4y1 plus y2, and all that we multiply by h. So it turns out that there is a nice formula, just like as long as you know the base and the height of this rectangle, or the basis and the height of this trapezoid, in this case the same thing. As long as you know these coordinates of these points, you'll be able to find the area under that parabola. So what does that mean? Let's do a quick example. If I give you a parabola that passes through the points 1, 3, 2, 7, and 3, 4, and if you try to plot this parabola, let's see if we can. So 1, 3 is, let's say here, 2, 7 is going to be here, and 3, 4 is right here. So it's like a upside down parabola. So it's going to look something like this, right? And if the question is, what is the area underneath this parabola, like this right here? What is this area? Well, we actually have the formula for it. According to the formula, the area is equal to 1/3. Then we're going to take the y0. So y0 is 3 plus 4 times y1. y1 is right here. It's going to be 7. And plus y3, y2, which is 4. And we're going to multiply it by h. h in this case is 1, because the two endpoints are 1 unit apart from the midpoint. And that's it. So we got the arithmetic expression that we can compute. 28 plus 7, 35. So the answer is 35 over 3. And you can check this, but to check this, you're going to have to find the equation of the parabola first using algebra. You may have to solve a system of equations there, and then after you find that equation, then you can integrate it. But this formula gives us the answer much faster. So what is the idea behind the Simpson's way to approximate the area under some function f of x on the interval from a to b? Simpson says that we can take an interval from a to b and divide it into even number of subintervals. It has to be even because otherwise we won't have enough intervals to build parabolas. So the last xn, n must be even. And when you have an even number of n's, you can split your intervals into like this triplets, and then you can combine these triplets, and on each of this, for each of these 3 points, you can approximate that piece of a function with a parabola. So we basically have one parabola over here. So this is going to be one parabola approximating this area. This is going to be another parabola. and so on and so on and so on. And hopefully you now see that we do have to have an even number of intervals in order for us to be able to create this parabolas. And what's going to happen next is we will be able to find the first area. So this area is 1/3. And now I'm just going to use the following notation. So yi is just f of xi. So here, instead of writing f of x0, I'm just going to write y sub 0. So y sub 0 is the height of this. y1 is the height of this. y2 is the height of this. And all that we multiply by h, where h actually is delta x. So this is the area of the first, the orange region, approximated with the Simpsons method. And now let's approximate this one. So this one will be 1/3, and now the first one is y2. So we're going to have y2 plus 4y3 plus y4 times delta x, and so on. And if we continue doing this, the last one will be approximated by this expression. It's going to be y3 yn minus 2 plus 4n minus 4yn minus 1 plus y sub n times delta x. And as you can tell, all of these expressions have a lot in common. So what we can do with all of them is we can take out 1/3 and we can take out delta x. And what's going to be left is we're going to have one of the first y, then we're going to have 4 of the next one, and then the next one we're going to have 2 of. But then the next one we're going to have 4 again. And then the next one will be combined with another one over here, so we're going to have 2 of the next one, and it's going to keep alternating between 2 and 4, 2 and 4. So at the end we're going to have 2yn minus 2, we're going to have 4yn minus 1, and we're going to have the very last one, y sub n, and it will be by itself. And what does this remind us? It reminds us a formula that we created earlier for the trapezoidal approximation, right? So let's summarize the formula for the Simpsons approximation. So n must be even. We're going to have 1/3 in the front. We're going to have f of x0 plus 2f of x1 plus 4. Oops, I'm sorry. We're going to have 4f of x1, 2f of x2, and so on. So it's going to rotate between 2 and 4, and then at the end we're going to have 2f of x n minus 2. We're going to have 4f of x n minus 1, and we're going to have very last one, f of xn, and we're going to multiply all that by delta x. And this is what we call the Simpsons rule, or the Simpsons approximation. And again, it's not the formula, but the process that matters here, although you should be able to recognize this formula. So let's try to use this approach, and let's do this problem. So we have to use the Simpsons rule with 2 subintervals. 2 subintervals means, well, it's going to be 2 subintervals times 2, so altogether we're going to have 4 subintervals here. So I would think but at two subintervals is actually two subintervals. So let's just treat it literally as two subintervals. So we're going to have an interval from 1 and 5. Two subintervals means we can find, so A is 1, B is 5, N is 2. Delta x is B minus A over N. 5 minus 1 over 2 is 2. So we got 1 plus 2, 3, 3 plus 2, 5. So this is my delta x. And at 1 we have 6. At 3 we have 40. And at 5 we have 114. So again, we're going to have y1 here, or rather y0, y1, and y2. And according to the Simpsons rule, so here we're going to be doing S2, the area is 1/3 y0 plus 4 y1 plus y2 delta x is equal to y0 is this one, y1 is this one, and y2 is this one. So y0 is 6, 4, y1 is 4 times 40, and y2 is 114. So we have 160 plus 120, that's 280. 280 divided by 3 is 93.3, and we would round it, right? So this was very simple. So let's do the same problem, but let's make it more intervals. So let's make it 4 subintervals. Now, if we're going to make it 4 subintervals, let's see what's going to change exactly. N becomes 4. So now we have 5 minus 1 over 4. That's 1. That means now we're going to have more intervals. So now we're going to have intervals like this. And we're going to have y0, y1, y2, y3, and y4 over here. And to find the S4, we would use the formula. It's going to be 1/3, and I'm just going to write it out, y0 plus 4 y1 plus 2 y2. And again, I'm going to rotate between 2 and 4, or alternate between 2 and 4 until I hit the last element, right? So 2y4, I guess that was it, right? So there isn't 2y4. So it's just going to be 1y4. All that times delta x. So plugging everything in, we get y0. And of course, we don't have y0 the same. I mean, y0 is the same, but y1, y2 are different now. We get 6 plus 4 times 18 plus 2 times 40 plus 4 times 72 plus 114 times delta x. Delta x is now 1. Let's see what we're going to get here. We get 1/3. 6 plus 72 plus 80 plus 288 plus 114. And so that's what, 402. And we're going to add 158. So it's 560, and we divide this by 3. Oh boy, 560 divided by 3 is 540. So it's 186.66, something like this, right? So this is how we use the Simpsons formula. All right, let's do another example. In this case, we have 4 subintervals, so the Simpsons formula will be as 4 1/3 y0 plus 4y1 plus 2y2 plus 4y3 plus y4 delta x. In our case, delta x is b minus a over n, 4 minus 0 over 4, which is 1. And let's find y0, y1, y2, and so on. So we start at 0. So this is my y0. This is my y1. This is my y2, y3, and y4. So it's pretty clear from the picture what the values are, and we can plug it all in. So we get 1/3 5 plus 4 times 5 plus 2 times 1 plus 4 times 1 plus 7 times 1. 5 plus 20 plus 2 plus 4 plus 7. And we got 25, 27, 34, 38 over 3. So 12.67. So this is how we use the Simpsons method to approximate the area under the graph of a function on some interval from a to b.